So the rational roots theorem is nice. It gives us a list of all the rational roots we could possibly want. If it's not on the list, it can't be a rational root. But the lists are kind of long. Like we've seen lists that were 12 numbers long, 16 numbers long. It'd be nice if we could narrow those down. So the rest of today's technology, DROS and the upper-lower bound theorem, they are tools for narrowing down your list as you go. So our first tool, our favorite crusty old French dude, is back to haunt us with another mathematical discovery. It's easier to show you than to try to write it out. So let's say f of x equals this. Why didn't I write this before I started the video? 11x minus 6. So here's our polynomial. What Descartes talked about is something called a sign change. And it's really simple. It's where this term's positive, right? We go from positive to negative. That's a sign change. And then we go from negative to positive, and positive to negative, and negative to positive, and positive to negative. So René Descartes would say that we have 5 sign changes. Where he's going to go with that is what he would really like to say is, therefore we have 5 positive roots. Unfortunately, that's not correct. See, the problem is René Descartes was doing his work at the beginning of the 1600s, and complex numbers, we had an inkling that they were out there when Descartes was alive. We had an inkling that they were out there and they were going to cause us trouble down the line. But we didn't actually formalize complex numbers and work with them algebraically until the late 1700s. So they were after Descartes' time. So his problem was, he could say, oh, I have 5 positive roots, but maybe some of them are these weird false positives, and I don't know what to do with those. What he was seeing was pairs of complex numbers. So the possibilities are maybe he's correct and we have 5 positive roots. Or maybe some of them are secretly complex numbers. Maybe they're not all real. If one of them is a complex number, here's the thing. Complex numbers always come in pairs. So if they're not 5, there must have been 3, right? 3 positive and 2 complex. This is the symbol for complex numbers. It looks like a cent sign, but it's not. It's a C with a slash through it. But that's not the only option. See, there's room for another pair of complexes. So maybe instead there's only 1 positive and 4 complex numbers. That could also be the case. There, I drew it a lot better this time than that. I'm going to redraw this. The complex number symbol looks more like, yeah, that's not so bad. It's a C with an extra line in it. So there's 3 possibilities. There could be 5 or 3 or 0 positive roots. It's not a wonderful system, but it's the best we've got. And it narrows things down a lot, because now it's like, all right, I found a positive root. Maybe I'm done. But if I find a second positive real root, then I know for a fact there must be a third. If there's 2, then there has to be 3. If I find 3, maybe I'm done. Or maybe there's more. If I find 4, I know I can't stop at 4. I know there has to be a 5th. So Descartes' rule of signs can give us some hints as to whether I'm looking at my list of rational roots. Do I want to test a positive one or a negative one next? Where am I more likely to find something? Descartes' rule of signs is your go-to, because it also gives you a trick for negative roots. Let me do a different example here. Let's say g of x equals x to the 4th plus 5x cubed minus x squared plus 3x minus 2. How many sign changes are there? 1, 2, 3. Positive to negative, negative to positive, positive to negative. This is not a sign change because it goes positive to positive. Just a side note, your polynomial has to be in standard form for this to work. You have to have these written in order. If they're not written in order, it don't work. So biggest degree to smallest. I'll be honest, I don't know why Descartes' rule of signs works. Almost everything else I've shown you in this class, I know exactly why it works. Descartes' rule of signs is a black box to me. I tried to read his work, but one, it's written in Latin. Two, he doesn't have any symbols. Symbol algebra wasn't done until after Descartes' time. He wrote everything out in complete goddamn sentences. So he would say, the fourth power of the number, summed with 5 times the third power of the number, subtracted from which is the quantity of the square of the number, and it just makes for horrible reading. So no, I actually don't know why this one is true. What I do know is there's a fun way to gimmick it, right? There's 3 positive real roots, so there are either 3, or maybe there's a pair of complexes and there's 1 positive roots. So I know there's at least one. If I haven't found any yet, I know I'm going to find one. For a fact, there has to be at least one. Maybe there are 3, but there's definitely at least one. So I keep looking. Once I've got 3, I mean, this guy, it's a 4th degree, so it has 4 roots. But if I found 3 positive roots, the other one's got to be negative. It can't be positive again. Make sense? Here's a funny gimmick. Negative roots of g of x are the same as positive roots of g of negative x. Get it? If I plug a negative number into here, it's the same as if I plug negative 4 in here, it's the same as plugging positive 4 in here. It's exactly the same thing. So if I do d Ross with g of negative x, which is negative x to the 4th is x to the 4th. Negative 5x cubed is negative 5x cubed. X squared don't change. 3x changes. Negative 2 don't change. All the odd ones change over. All the even ones stay. Because the even ones, it's like, oh, I plugged in a negative x. So there's 4 minus signs in here, and they all cancel out. But x cubed, it's like I plugged in a negative x. Okay, a pair cancels out, and the last minus sign comes out front. X squared, 2 cancel out. X, 1 come out front. Negative 2, there's nothing at all. So all of the odd terms get switcherooed. All of the even terms stay the same. And now I count the sign changes. Positive to negative, there's only 1. So I know for a fact there has to be exactly 1 negative root. So then I make my list, and my list goes, geez, what is it? It's possible that 2 is a root, or 1 is a root, or negative 2 or negative 1. Actually, the rational roots theorem is a really short list. 1, 2, negative 1, negative 2. So I would check to see if any of those rational roots go in. 1 doesn't work. Negative 1 might work. I don't. No, negative 1 doesn't work either. Does 2 work? 16. No, 2 don't work. Maybe negative 2 works. Nah, negative 2 don't work either. Okay. So all of the roots this time, we got unlucky. There's going to be, I don't know, there's going to be a negative root and there's going to be a positive root. They have square roots in them and they're terrible. And then maybe the other 2 roots also have square roots, or maybe they're complex numbers. Either way, no further I can go with this. We're done here. So that is Descartes' rule of signs. Same René Descartes who gave us the Cartesian plane. Brilliant mathematician. I'm sorry for calling him a crusty old dude. I mean, they're both true, but I'm sorry. Okay, here's a couple more things about the DROS, which is what I'm calling Descartes' rule of signs because it abbreviates to DROS, so I just call it DROS. Let's say g of x is 2x to the 6th minus 5x to the 4th minus 3x cubed plus 7x squared plus 2x plus 5. Hey, here's an exercise. Do the DROS. I'll let you pause the video. And unpause. How many sign changes did you find? Positive to negative, negative to positive. That's it. So either 2 or 0, positive roots. Now let's make g of negative x. We get 2x to the 6th. 5x to the 4th don't change. The cube changes. That becomes a positive 3x cubed. The even don't change. That stays 7x squared. 2x, that changes. Negative 2x. 5 don't change. So how many are there now? A 1, a 2, a 3, and a 4. So there are 4 or 2 or 0 negative roots. The pattern is you start at your number and you just go down by 2s until you run out. So up there it was 5 or 3 or 1. Down here it's 4 or 2 or 0. You just keep going down by 2s all the way until you get to 0 or 1. And now this is a 6th power. It's got to have 6 roots. And so I know that 4 or 2 or 0 of them are negative and 2 or 0 of them are positive. Because unfortunately this is René Descartes' tool, and he couldn't find a way to incorporate complex numbers because he didn't really know what they were. And it's been hundreds of years and we still haven't found a way to incorporate complex numbers into it. So this is as good as it gets, basically. If someone were going to fix it, they would have by now. It's not possible, I assume. Like I said, this is one of the very... In fact, I think this is the only thing in the course that I just don't know how it works. It's just magic to me. Maybe someday I'll learn it, but... No, I've honestly, I've seen some of the proofs that go into things like this, and I have a feeling it's very bad. I have a feeling it's very bad. Okay, I want to make one more point about DROS, and then we'll leave it behind until the end of the lecture. One more point about DROS. If I say k of x equals x squared minus 2x plus 1, I've got 2 sign changes, so there are 2 or 0 positive roots. And I also know that there's 0 negative roots, but that's not important right now. But the thing is, I can factor k of x. X squared minus 2x plus 1 factors as x minus 1 times x minus 1, or x minus 1 squared. So there's only one root, and the root is x equals 1. So what gives? I said there would be 2 or 0, and there's only one of them. Well, this is a root of 1 with a multiplicity of 2. The factor shows up twice, so that counts as 2 positive real roots. So all of these numbers that I've shown you with DROS, they count multiplicity. It's unfortunate, but it's just the way it is. They count multiplicity. So x minus 1 twice counts as both positive roots. That's just how the tool works. When you make a tool in math, it's like if you write a song, you can write the song by yourself, or you can do like a collab with another artist. But when you're doing math, it's like you're always doing a collab with the universe, because it has to be designed for what you want to solve, but it also has to make logical sense and be consistent with the rest of mathematics. That's not something you get to choose. So Descartes, it's half like you invent it and half like you discover it. Math is, when you're doing new math, you're inventing and discovering always at the same time. So it's a neat invention, but the discovery aspect, it was impossible to make it any better than it is. I assume. Like I said, for something that's included in college algebra, I think this century there's been like one new discovery in mathematics that actually gets taught in undergrad courses, and the rest of it is all grad school stuff. Undergrad math is basically solved at this point. And it had to do with matrices. So plug for linear algebra, it's a lot of fun. I'll tell you more about linear algebra in section 11.1, so that's much later in the course. But okay, let's break the video into another part.